our next speaker will be Kaushik Chowdhury. I hope I pronounced this properly, yes. So he's from the Northeastern University. So Kaushik received a PhD from the Georgia Institute of Technology in Atlanta in 2009, continued in research, and now is a professor and associate chair of research at the Electrical and Computer Engineering Department at Northeastern University. His expertise and research interests in general are wireless cognitive radio ad hoc networks, resource allocation and wireless multimedia sensor networks, and biomedical applications of sensors. And Kaushik now will present to us AI and ML Open RAN using OpenAirInterface.
Well, thanks for having me here. Thanks for the introduction. I thought you were about to say that here's Kaushik Chowdhury, who never had a real job in his life because he graduated from Georgia Tech and then straight into academia. So my apologies if I come from that angle. So in all disclaimer, I am new to the OAI world. Okay, I come from a more sort of a more spectrum applied machine learning research, and I'm trying to learn how can I merge these two very, I wouldn't say very different, but certainly very complementary technologies and get something really exciting out of this. So that's where I'm coming from. So what I'm going to do today is tell you things that are on my mind, things that I feel are important, some initial trials that I have started to do, and I'd love to get your feedback on some of the open challenges that you think that might make a difference for more widespread adoption of this technology. So with that said, so when I look at the ORAN architecture, I look at all these disaggregated components and these functional blocks that are each doing an individual role. Now, my take on this is going to be data centric. So I'm going to be worrying about what is it that, or how well is the inference happening in the near real-time rig, and what would be the impact of other latencies that might impact this the quality of the inference or the timeliness of this inference. And not only that, I also want to understand what is the overhead of this data that is being relayed from the G node B to the near real-time rig. And if I stress that interface much or large enough, what would happen to the way in which I'm running the rest of these steps? Okay, so I'm coming in from a data side of things. And finally, I want to talk to you a little bit about training these machine learning models and in the non-real-time rig, and some of the tools that we have developed in general for data collection, and if some of these could be incorporated into a data collection framework. I'll conclude with an example of if all these things are there, then what more we could enable using ORAN. All right, so first is some very high-level insights on the impact of encryption on the E2 interface. Okay. So yes, I'm completely subscribed to this, to the benefits of ORAN in terms of virtualization, disaggregation, and open interfaces. Now, when you talk about open interfaces, there is always going to be a concern that are these secure? And in fact, the ORAN Alliance has come up with some guidance on it, and it in fact says that this E2 interface must support confidentiality, integrity, replay protection, and data origin authentication. Right. So these are classic metrics that we teach in our graduate level networking courses as well, but these metrics are important in securing the interface. So now when you talk about these metrics, and this is a graphic taken from NIST, it's not a unilateral optimization. So there are multiple dimensions that we must optimize. So for example, what is the cost of doing this? What is the performance hit you're going to get? And for the assurance of security. So these are these three axes that we want to understand a little bit more and explore. All right, so a quick mention of ORAN implementation in the Colosseum. So we have a speaker right after me, Michele and Tommaso have, and his team of researchers have an awesome implementation of OAI in the Colosseum. So they're going to tell you more about the details and the underlying structure and how they've implemented it. But this is at a high level, and you can go read that paper as well. But this is a high level implementation of what they have in the Colosseum. On the right-hand side, you see that each of these components are instantiated as LXC containers that are running in individual nodes. And they have designed an E2-like interface that actually connects the G-Node B to an open source adaptation of the near real-time rig. So again, Michele is going to be the right person. Michele, where are you? There. He's going to be talking right after this. So he'll tell you, he'll give you the deep dive into how he's done this implementation. All right, so now what I'm going to do is I'm going to look into this a little bit more, this particular E2 interface a little bit more. And just to sort of secure it, we have done something very preliminary. We have implemented IP security protocol. And what we have done is and within IP security, you have two options. You have authentication header, or you can go with encapsulating security payload, which is the ESP. We have implemented this in the tunnel mode. And again, you have multiple options of what authentication mechanism that you want to implement. So we went with the AES 256 and the SHA-2 256. One does encryption, other one does sender authentication. Okay. Again, these are well-known details of these two protocols are well-known. Now, when I start to look at the effect of all these different processing and the data transmission delays, the queuing delay, the propagation delay, I start to see that they start adding up. Now, luckily, if I just do the math, I find that so far, I'm not really taking a hit. These numbers are fairly small. So what you see here in the, I've just ignored the queuing delay. This is just a single point-to-point. There is not much traffic out there. So I'm ignoring the queuing delay for now. The transmission delay is, again, fairly small, and that is because we have implemented the X2 application protocol, which is generating two packets, a smaller X2 app packet and a longer X2 app packet. In either case, with a 10 gigabits per second Ethernet cable, we can deliver them fairly fast, right? So it's really, the propagation, the transmission are not really the dominant factors in this end-to-end delay. So what are the other factors, right? So in this example, then what we do is we set up a ICMP ping, and what we're doing is we are trying to measure the end-to-end latency of the round trip time where the ping packet is sent and the reply is received. And so what you see here are two plots. On the red line, you see the ciphertext. That means this is where I am actually doing the encryption, and the black line is showing you the plain text, where basically I'm not doing any encryption on the packets. So if I just sort of repeat the math a little bit, essentially what you see is that the processing time is roughly about half of the round trip time in this particular Colosseum example. We assume about 100 meters of cabling across the G-Node B and the near real-time rig. So you can see that now there is some amount of impact of this encryption that you see on this end-to-end delay. However, this is still in the range of around microseconds, right? So it's still not affecting me that much. So this is all very heartening that I can run this without worrying that the encryption is not going to kill these end-to-end latencies. So we wanted to measure what is the impact on throughput. Now for this, we set up iPerf3, and we are essentially increasing the packet, the attempted transmission rate from about 25 Mbps all the way up. And you find that for the Colosseum implementation, if we just do the plain text method, it works pretty well for fairly high attempted transmission rates, but it sort of breaks down, as you can see in the red line, for around 500 Mbps or so, or 475 Mbps to be more precise. So to deep dive into this further, we started to look at the CPU utilization, which is essentially the compute process that is doing the encryption and the decryption process. And here is where you see the hit. And so here is what you see is, so on the left side, you see the throughput without, or rather the CPU utilization when you have no encryption, and that's the throughput increases linearly as you see with the attempted transmission rate on the x-axis, and the CPU utilization in the blue dots or the blue crosses, you see it's also sort of increasing linearly. But on the right-hand side, that's where you see that around 475 Mbps or so, you see that the CPU utilization has sort of saturated. So this is really what we have to be careful about. We, as we start to design these systems, this is going to be the bottleneck. It's not so much as the data rate that you are carrying on these interfaces, but what kind of CPU resources are you using to do this encryption? All right, so the takeaway message is that CPU utilization is a key trade-off in this 3-axis optimization that you're trying to do. In general, this is still a good sign because overall the cost of securing the E2 interface, at least for this very limited initial test we have done in the Colosseum, is fairly, it looks fairly promising. So if I go a little bit further down, I want to talk to you about an effort that I'm involved in called as RF Data Factory. And for this is an NSF funded project. And the goal here is to simplify data set collection. And so to be honest with you, it's hard to create good data sets that can be reused, data sets that can be, that are really representative of a variety of problems. So for this, what we have done is we have built a framework, and we are trying now to put this into a system, into the ORAN framework, and we're exploring what would be the hooks, what would the changes that need to be done in this framework. So I'll tell you a little bit more about this framework in just a bit. So our goal is to create this data collection framework and push it into the non-real-time rig once these other interfaces are better available, and make this as a tool for researchers. Now, what is RF Data Factory? This is basically a one-stop resource for the wireless community. You can go and download data sets on a number of different topics. You can download software APIs that will allow you to create these data sets. And also there are tutorials that allow you to share and even sort of know how to represent these data sets in a standards compliant manner. And we have adopted the SIGMF as our preferred format going forward. So in all of this, and you can go to rfdatafactory.com, there's a bunch of resources already available. So our goal here is to create these data recording APIs. So for this, we have partnered with National Instruments, and shout out to our colleagues at National Instruments, Vincent, Abdo, Michael, and Charles, and others. And so what this API does is that you just specify some high-level directives, and you say that these are the channels, these are the say perhaps the sequence of channels you want to switch. These are the recorded waveforms you want to play back, etc. And these are the number of radios. The system auto configures a number of these different SDRs, initializes them, executes this entire data collection platform. You can do it over the air, you can do it over wires. It self-calibrates, it generates the data that it generates, it then captures and splits into appropriate folders with SIGMF compliant metadata already incorporated. So this is an auto one-button push to collect data sets. And we are wondering if something like this would make sense for a data collection tool eventually to be integrated into a more, and this is all open source, by the way, you can go download it, right? We're just wondering what we can do to integrate this further and sort of give back to the community. So this is an example of what the metadata format looks like. So I won't go into these details. There's lots of little wordings in here. And for some reason, this community loves acronyms. Okay, so there are a bunch of these acronyms in there too. But essentially, these are, it's just supposed to make life easy. Now, the final take here is, all this time we have looked at how to use data in optimizing network functions, but can the network itself become a source for data? So for that, with that in mind, I have a use case. we know how important the spectrum shortage is. And so the Citizens Broadband Radio Service Band, or the CBRS band, is one way out, that in the 3.5 gigahertz band, commercial operators can coexist with incumbent naval radar, right? So at least that's the theory. And so, of course, you need a series of environmental sensing capabilities that, or ESC sensors along the coast, that are sampling this or sensing this information and giving this information back to the SAS to sort of record and then coordinate the actions of the operators. Now, in all of this, you see that there is a whole bunch of infrastructure that is lined up, that is specially designed and deployed for this purpose. So the natural thought is that, why do we need this dedicated infrastructure? Why not reuse an existing cellular infrastructure and enable the same functionality? Now, if you can do that, the benefit is that you can do more than just naval radar. You have a vast deployed network of base stations all around, but you need to get them to be programmable to now switch from comms only to sensing slices and perform other adaptations by using machine learning. So what have we tried to do in this space, right? So that's the vision. And so what we have done is, we have used these APIs that I just discussed, this API that we jointly worked with National Instruments on, and we created some of the first over-the-air data sets on where we have LTE overlapping with Type 1 radar. Now, the goal is not to say that, or rather to look at these marginal cases where you have granted permission to an LTE network, and the radar comes in after some time, and you now need to detect that this has happened, right? So could we use things like machine learning to detect very weak embedded radar pulses within a larger coexisting or overlapping LTE frame? And if you can do that, then there is a possibility you could reuse your base stations for something like this. So we have used a very famous image detection framework, or object classification framework called You Only Look Once, or YOLO. And we have extensively collected data on a number of these different sort of testing modules. So what you see in this chart here, in this table here, is TM1, and then going down to TM33. These are nothing other than different types of test cases of LTE frames with different amounts of resource blocks. So they actually look different in a spectrogram. And when you superimpose these radar pulses inside, the challenge is that, have you trained them robustly enough, right? Have you trained it on a large enough representative data set? So anyway, so we have done this, and you can see in precision and recall numbers, we are doing fairly well detecting LTE presence absence and detecting radar presence absence. Now, this is where we want to take this further. We want to take this and create a sensing slice using ORAN. Take this basic proof of concept and deploy this on a system. Now, just to conclude, we have done, there is a lot of interest in designing machine learning machine learning XApps for ORAN, and that is, the community is excited by it. However, we need to understand the overhead of relaying this data with some security considerations, and nothing comes free in life, and we have to be cognizant of that. We need to stress test the effect of these interfaces. We have just done something, we have just scratched the surface, but a whole lot needs to be done. We need to consider seriously the data collection process and the data training process, and the variety of considerations that will go into this. And we need to create especially metadata that is easy to use, understandable, and share. And finally, ORAN can do much more than communications. And so this distributed sensing is a whole, I wouldn't say very new, I wouldn't say that no one else has thought of it, but this has certainly not been the mainstream thought. But we would love to see more of that in further discussions. All right, with that, I'll stop here, and thank you for listening to me.
Thanks for the talk. I really like that idea of sensing and integrated sensing in the world. Joint communication sensing seems to be making its way into 6G, and so I think it's important for OAI to think about it too. So what I mean, have you talked a bit about the details? What needs to be done in OAI? How this could be integrated? Do we have an E2 node that does sensing? Or
It's exactly that. So what we're trying to do is we're trying to create sort of sensing slices is what I call, where we are saying we are quietening down. We are saying all the other UEs. Sorry, I should go down. Yeah. So I think the question is that have you really started to do something about it? Yes, you gave a vision, right? What are you doing about it? So yes. So what we're doing about it is that we are trying to think of this as creating slices, and the slice involves the XR basically tells the G node B, go quieten your UEs and as much as you can. And in that system, we calibrate against noise. We establish a background level and see that, okay, this is the background noise level. And then once the system starts again with regular comms, the intent is that the UEs should just continuously transmit. And if there is someone else, a radar that is being transmitted, I will, I am siphoning off, I'm creating spectrograms in the G node B and sending those up. And then trying to do spectra, run YOLO on the spectrograms, and with some probabilities detect there is something there. If so, then I send back a directive to the G node B and says, UEs, now you got to silence yourself for just a little bit because I need to be sure that there's someone. And so these are the sort of things that we're trying to do. Still very early, but yeah.
Very simplification. So one question I had is, so is the idea to create a E2 sensing pathway to spectrograms and ship it back up, or like have a different program interface that does that sort of shifting?
So we are hoping not to create a new interface, but to reuse what is there. So the question is, the question that I keep asking is the best way that I would like is that I could operate on IQ samples straight, but not possible, right? So for that reason, we are, it's not going to be fully compliant as you have today, but we just sort of create the spectrograms and ship it up.
So in the CBRS example, you said you quiet the terminal, you can listen. In the meantime, how do you continue the service?
No, the quieting of the terminal is only when I'm suspecting something is there. So my first round is my first round is always analyzing the spectrogram in overlapping LTE and radar. And only when I'm suspecting, my initial round of YOLO says with, say, a threshold probability something exists, then I need to silence and there is going to be a service disruption that would anyway be there, but I don't want to do it preemptively.
I mean, you're taking CBRS as a generic example, you're not following the rules of CBRS.
Well, in a way, well, the rules say that you should be able to detect radar and then stop or inform the operator, and the operator should stop within 60 seconds. There's a certain threshold power level and things like that. Right? I'm just simplifying this, but at core, these are the high-level goals.
I mean, at high level, it's not. I agree with what you're doing, but I think at high level, there's an external entity that is doing the detection and ordering you.
That's right.
Not the, I mean, you're not asked to do
You're not self-policing. That's absolutely right. There is the ESC sensors and the SAS which is doing it. Absolutely right. So the goal is do we need to be policed, or can the system? Yes, you're right that this is not compliant with the CBR's vision, but yeah. Well, thank you.